Okay, let's have example number 1. As one sample 10 centimeter in diameter is placed in a tube 1 meter long. A constant supply of water is allowed to flow into one end of the soil at A and the outflow at B is collected by a beaker, as shown in our figure. The average amount of water collected is 1 cubic centimeter for every 10 seconds. The tube is inclined as shown, so we have to identify or determine the average velocity of flow through the soil in centimeter per second. Determine the seepage velocity or the velocity through the void spaces in centimeter per second. Letter C, determine the coefficient of permeability of the soil in centimeter per second. So this is an illustration for our sample number 1. So we have an inlet and we have an outlet, and in the outlet we have a beaker to collect the water that comes out from the soil sample. So basically this illustration is a setup for constant head test. So for this one, we have to identify first the average velocity. So to get the average velocity, since we are given with the volume and the time, so we can divide that one so that we can compute for our flow of water or the discharge, which is 0.1 cubic centimeter per second. Since we have now computed for the discharge, from the formula Q is equal to A times V, we can compute now for the velocity. So velocity is equal to Q divided to the area. So that would be 0.1. Since the diameter of our soil sample is 10 centimeter, so we can have that 1.1 all over pi all over 4 times the diameter, which is 10 raised to the second. Simplifying this one, we have now 0.00127 centimeter per second. The second one is to solve for the seepage velocity. So of course we know that seepage velocity is equal to velocity discharge or discharge velocity all over n, which is our porosity. Since we are not given with n, our porosity, we are only given with E, the void ratio, we can have the relationship between porosity and the void ratio using this equation. So simply have to substitute the value for the void ratio, and we get now, if we try to simplify this one, we have 0.375. So we have now our n, the porosity. Substitute that into these equations, then we have now 0.00127 all over 0.375, so that we can get our seepage velocity, which is 0.00339 centimeter per second. So for that one, after that, we can compute now for our coefficient of permeability or the hydraulic conductivity, which is, we have to compute first for our, from this equation, Q is equal to Ki times A, we have to compute first for our I, hydraulic gradient. So based on our equation, H over L, our H is this. From the setup, you have our H, which is 2, this is 2, minus, okay, this is the surface, the inlet surface, this is the outlet surface. So basically our H is from the outlet, from the inlet surface towards the outlet surface, so that is our H. So since this is 2 meters, this portion is 0.8, so that would be 2 minus 0.88. So that is 2 minus 0.8 divided to L, which is the length of the soil sample, which is 1. You simplify this one, I, the hydraulic gradient is 1.2. So you substitute that into this equation so that you can compute now for the coefficient of permeability, and that gives us 10.61 times 10 to the negative 4 centimeter per second. The second example is a falling head permeability test. It has a given values of length of specimen 200 mm, area of soil specimen 1000 mm squared, area of standpipe is equal to 40 mm squared, head difference at time t, which is equal to 0, is 500 mm, and head difference at time of 80 seconds, which is equal to 300 mm. So basically, so we have to determine the K, or the hydraulic conductivity, for the soil in centimeter per second. So our equation is this one, so that we can compute our K. So we have to identify our A. which is 40 mm, the area of the standpipe, our L, which is 200 mm, the length of the specimen, our area of the soil specimen is 1000 mm squared, our T is 1/82, and our H1 is 500 mm, and our H2 is 300 mm. So basically from here, we can simply substitute our given parameters to this equation, and we can get our K, which is 2.27 times 10 to the negative 2 centimeter per second. So now we move on to the effect of water temperature on K. So basically, the water temperature affects the permeability in soil. Permeability is inversely proportional to the viscosity of the fluid. It is known that viscosity varies inversely to the temperature. Hence, permeability is directly related to temperature. So meaning to say, the permeability of a certain soil is directly related to the temperature of the water itself. So the greater it is being stated that the greater the temperature, the higher will be the permeability. So this means it is directly proportional. The temperature of the water is directly proportional to the permeability. So that is the main reason that seepage is more in summer season than in winter. So meaning to say, the higher the temperature, the higher is the permeability. The lower in temperature, the lower is the permeability. So it explains why there is more seepage during summer compared to winter. So that is basically the effect of water temperature on K. So the higher the temperature, the more the soil is more permeable. So this is the equation or mathematical expression that explains the effect of water temperature on hydraulic conductivity or permeability coefficient. Now we move on to the flow through permeable layers. So basically this one is the flow of water through permeable layers. So we have layer of soil, and how are we going to, this illustrates on how are we going to obtain the hydraulic gradient for a permeable layer that for a soil that goes through a permeable layer. So to compute for the hydraulic gradient for this kind of setup, for this kind of illustration of the flow of water through permeable layers, our hydraulic gradient I is equal to H all over L all over cosine alpha. So basically, we have here a soil layer, and we have a standpipe installed, and from this surface of the water of the standpipe to the surface of the water of the standpipe is our H. This is our head, and our L is from the center, from the distance from this one standpipe to the other standpipe. And of course, cosine alpha is the angle of inclination of our soil layer with respect to the horizontal. So you simply have to substitute whatever is the given values. You can find another value for the hydraulic gradient. So this is another illustration wherein to compute for hydraulic gradient for a flow through permeable layers. So we have here a water table. So we have a water table that is located within the soil layer, and to compute for our hydraulic gradient, basically that is I is equal to sine alpha. Alpha is the angle of inclination of the groundwater table with respect to the horizontal. So we have a sample problem. A permeable soil layer is underlain by an impervious layer as shown in this figure with K 5.3 times 10 to the negative 5 meter per second. For the permeable layer, calculate the rate of seepage through it in cubic meter per hour per meter, with if H is equal to 3 meters and alpha is equal to 8 degrees. So for this one, we're going to compute for the rate of seepage. So this is the setup for our permeable layer of soil. So we're given with our H, we're given with the alpha, and we're given with our K. So this is now how the setup for our given sample problem. So this is basically from our H, which is 3. So you can have this as 3 cosine alpha, and this one, of course, alpha, which is 8 degrees, and this distance is equal to S tangent of alpha, and this one is our S all over cosine alpha. Our S is the distance. This is the distance. This is the horizontal. S is the horizontal distance. So if we're going to have our I in our equation, which has head loss all over length, so basically our head loss is our S tangent alpha from this figure. Our head loss is this one. So basically, if we're going to have this horizontal, from the surface towards the surface, that is our head loss. So that is equivalent to S tangent alpha, and our L is the length, which is equivalent to this one. This is our length, which is S all over cosine alpha. So the length of the soil sample, that is S all over cosine alpha. And basically, if we're going to substitute, you can have, if you try to simplify, that is sine alpha. So from the equation, which is Q is equal to Ki times A, we simply have to substitute our given values for K, for alpha, and we can now obtain the value of our rate of seepage. And we have changed this to, which is given as for this one, change this to meter per hour. So we have 3,600. So that means if you try to simplify this one, you get a value of 0.0789 cubic meter per hour per meter. So that is now for our second example for this one, wherein we have to calculate the rate of seepage for this permeable soil layer. So that's N for flow of water through permeable layer.